Hi everybody, it's my birthday. I'm here by myself in the library, so I thought I'd dress appropriately. It's going to be the deal today. So, we're talking about the Bohr model of the atom. And just to recap a little bit, keep everybody on the bus here. Back around the turn of the 20th century, it was discovered, or it had been known for a while actually, that when you light up an element like hydrogen, it doesn't produce a nice continuous rainbow spectrum. Okay, it produces only discrete colors. That is, discrete wavelengths. And I'm actually going to write these wavelengths down again. I wrote them last time. I had to erase the board. It's a new day. Feels the same to you, but this is Friday, April 17th. So I'm going to rewrite these down here. The lines are 656.3 nanometers, 486.1, 434.1, I don't have these memorized, believe it or not, and 410.2. These four different colors, these are the wavelengths. Okay. This is the longest wavelength, the red one, of course. Over here, I don't have nice deep purple markers, but the deep purple ones, 5 and 6, are the 434 and the 410. All right. And so these lines, we call them lines, but they're really just wavelengths, show up when you light up hydrogen gas, and nobody knew why until Mr. Niels Bohr came around and figured it out. That's what we're going to get to here. Balmer came up with this formula here, and basically this was a mathematical formula. He just played with numbers, messed around with numbers, and figured out that he could reproduce these wavelengths with this formula here. So a given wavelength, say for n equals 3, for the dark red wavelength here, that wavelength, 656.3, comes out of this formula if you use this constant, which he just adjusted to fit the data, multiplied by 1 over 2 squared, that's 4 of course, but we call it 2 squared, minus 1 over n squared. So if you put n equals 3 in here, if you put n equals 3 there, you will get 656.3 for lambda, and all the same for the rest. So this is n equals 3, 4, 5, and 6. Okay? Those wavelengths are the ones that pop out. And so we talked about Bohr's assumptions, and we talked about what came of his theory. The first thing here, and we'll say more about this in a few minutes, is that the size of the atom, that is the radius of the orbit, remember we assumed a circular orbit, the radius of the orbit of the electron can only take on certain values. For these formulas here, n is 1, 2, 3, ... And we'll see how these two n's connect in a second. Okay, so it could be a naught, the Bohr radius, or it could be 4a naught or 9a naught, because you're squaring in. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So the atom can only have certain sizes. Also, the atom can only have certain energies. And I tried to emphasize to you last time just how weird that is. How weird it is that the atom can only take on certain energies. It is exactly like, the weirdness of it is exactly like the weirdness of me saying my car can only go 0 miles per hour or 5 miles per hour or 15 or 25, but nowhere in between. Never will you measure it moving any speed between those. It's always moving one of those speeds up to say 95, after which my wheels fall off. But you get the idea. 10, 5, 15, 25, 35, 45, only certain energies are allowed, okay, to the atom, and those are given by these. And we'll say more about those energies too. But things are quantized. They can't take on any old continuous value. They only take up specific values. The third result that's important to us from the Bohr theory has to do with transitions. Okay, and we'll say what transitions are. Transitions are where you go from one state to another. Kind of going to drive in my car going 25, boop, 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 and all of a sudden, pow, I'm going 15. That's a transition from one state, the 25 mile per hour state, to the 15 mile per hour state. Okay, that's a transition. And the third result of the Bohr model has to do with transitions. And what his model came up with, this big third model here, was this. Well, let me see, I want to use, I think I'll use pink, just to keep things lively here on my birthday. Let's see, so 1 over lambda. This was the third result of the Bohr theory. There's a big old mess of constants out in front here. This is going to be a monster. The mass of the electron times the Coulomb constant squared times the charge, fundamental charge to the 4th power, all divided by 4 pi times the speed of light times h bar cubed. Now that is a nice big mess right there. All of that times 1 over n final squared minus 1 over n initial squared. This came out of the Bohr theory. The theory we talked about in video 6 and 5 too, I think, for that matter. Now this is a mess. Okay. A couple things to say about it. One is when I talk about transition, is from one state to another state. Like again, me driving my car, I'm going 25, and then I transition down, boom, into the 15 mile per hour state. So there's an initial, so this is a transition here between Ni and N sub f. The initial value of N to the final value. Then it might be from 3 to 2, it might be from 7 to 1. Right? Each one of these N values, as I have said in previous videos, is a state. So we're going from a higher state to a lower state. Could be 5 to 2, could be 3 to 2, could be 2 to 1, could be 8 to 4, whatever. We're going from a high state, N equals a high number, to N equals a low number. Like me slowing down in my car, going from 25, boom, back to 15. Okay. So this looks like a big mess, but the interesting thing here is, and do listen closely, is that this quantity here, this big mess right here, which you'll probably never see again in your life, has a value. That value is 1.097 times 10 to the negative 7 inverse meters. In other words, it is equal to the Rydberg constant here. When Bohr figured that out, he knew he was on the right track. Okay, so the last result, the third result, we can rewrite it, and I will rewrite it right now. This way. Wish I had a bigger glass board to deal with, but I guess you can't look a gift horse in the mouth. Isn't that the old weird saying? So, this is a nice studio here, actually. I'm quite grateful for it. So, what we end up with is 1 over lambda equals r sub h, the Rydberg constant right there, the same one, times 1 over n final squared minus 1 over n I squared. Okay? That is the third conclusion. Okay? The first one has to do with the size of the atom, the size of the orbit of the electron, which is basically telling you the size of the atom. The second one has to do with the energy value at each one of those sizes, each one of those n values are each called states. So the first state has a given radius, a given energy. The second state has a different radius and a different energy. The third, n equals 3 third state has yet a different radius and a different energy. Okay. And when the atom transitions from a higher state to a lower state, it emits light of these wavelengths. So if it goes from n equals 8 to n equals 2, we can calculate this and get the wavelength. That's the color of light it emits when it goes between those two states. Okay. So what I'm going to do now is I'm going to draw a couple of diagrams for you in the next couple of videos. The first one's going to relate to this picture here. And the second one's going to relate, the first one's going to relate to this equation here, the first result. And the second one will have to do with the second result. And then I'm going to show how the third result, the one in pink here, connects with those pictures. I'm going to give you a visual image, two visual images really, okay, of the atom for you to think about. Okay, that's coming up next.